Right. Yes. So, right. So today will be a short talk, and the goal. I have two goals. The first is to understand the category of vector bundles and the syntomification, which I guess we already briefly discussed last time. And I also want to say something about Poincaré duality for syntomic cohomology. And in particular, maybe one reason why I might care about understanding this category of vector bundles is that, well, this tells you more explicitly which kind of coefficients are allowed in these comparison theorems that I had at the end of last time. Okay, so let's start with part one. And for this, maybe let's recall that if X is a smooth rigid space over QP, then Scholze has defined a sheaf OB Duran on the proetal side of X, and this is a filtered B-Duran algebra, and it's equipped with a B-Duran linear connection. And using this, we get a factor from filtered vector bundles with connection on X. And so when I say filtered vector bundle with connection, so filtered vector bundle will always mean that the filtration is locally by direct summons, and the connection is always supposed to be transversal to the filtration, so it maps fill I to fill I minus 1. And this goes to the category of B-Duran plus local systems. On X proetal. And the functor takes such a filtered vector bundle with connection and maps it to, I take my vector bundle B and I contend that over OX with OB Duran. So maybe I should also have said that OB Duran is also the OX vector. And then using the connection I have on E and the connection I have on OB Duran, I get sort of a tensor product connection in this thing. And I take the kernel of this connection. And then I also have a filtration on E and a filtration on OB Duran. So I get a tensor product filtration on this thing, and I take the fill zero piece. And the claim is that this is a B Duran plus local system. Okay. And
this is a fully faithful functor.
I was about to say that, yeah. So what Scholze proves is that this is fully faithful. And I want to call a B-Duran plus local system, which is in the essential image, generically flat. Okay. Then I make the following definition. So if I have a vector bundle on the Fark-Fontaine curve of the diamond of X, then I call it Duran if it's pulled back to the formal neighborhood of X diamond. So remember that, well, where X is over QP, so there's a map from X diamond to Quark-Fontaine X diamond. If this identifies with a generically flat Biederam plus local system. So vector bundles on this formal completion will be Biederam plus local systems, and I'm asking that the Biederam plus local system I get be generically flat. Alright. Maybe let me say that in particular I can restrict to vector bundles which are semi-stable of slope 0, and this is exactly the category of the round local systems. So the round local systems, they embed fully faithfully anything. Well, I guess I haven't introduced a notation for this category of the round vector bundles, but I will denote it like this. Okay. Alright. And then the theorem that I think I orally stated yesterday already is that if X is, well, I have to make the additional, well, still in this situation where X is a smooth rigid space, but I have to make the additional assumption that X is partially proper, because in this analytic prismatization and syntomification business, we're always working with Berkovich spaces, and so only for partially proper rigid spaces I get a fully faithful embedding into Berkovich spaces. So if X is in addition partially proper, then I can identify the category of vector bundles on the syntomification with the category of Durand vector bundles on the Quark-Fontaine curve of the diamond of X. Okay. And so maybe let me also state one consequence. So last time I also gave a description of vector bundles on X syn in terms of sort of vector bundles on the Hyodo-Kato stack and the filtration. And if you combine these two segments, then you see that this category of Durand vector bundles on Quark-Fontaine X diamond is equivalent to the fiber product of vector bundles on X Hyodo-Kato with vector bundles on the filtered Durand stack over vector bundles on the graph stack. Alright. And so this is again some kind of instance where via syntomic homology or via the syntomification you can relate like Durand data and Étale data. Okay. And so now let me say something about how you prove this equivalence. And so for this, also recall from yesterday that I had the second description of vector bundles on the syntomification via vector bundles on xdiff1. And then again, you need to add some filtration data. Where I recall that sort of this thing was the overconvergent neighborhood of x hot state inside of xdiff1, and this was xn, and then you restrict to the locus where t has non-zero. So it's a filtered version of this one. All right. And so what do we have to show? Well, we have to show that the functor from vector bundles on this filtered guy to the vector bundles on the unfiltered one is fully faithful. And that the essential image is characterized by this de Rham condition. Okay, so why is this enough? Well, recall that Arthur already mentioned in his talks that vector bundles on this X-diff1 are equivalent to vector bundles on Fark-Fontaine X diamond via pullback along. You have a map from Fark-Fontaine X diamond to X-diff1. And this induces an equivalence in vector bundles. Alright. So this is what we have to show. And now somehow you're supposed to make filtered vector bundles with connection up here. And for this, we make the following observation. So if I take this well, maybe I want to draw a picture. So I want to look at the filtered prismatization of X, and I want to look at the locus where the product of U and T has norm 0. So either U has norm 0 or T has norm 0. And this looked something like this. So I had this part where U has norm 0, and I said that this is just X de Rham plus. And then I had this part where T has norm 0, and this is this filtered over convergent Hodge-Taitz-Stark. Right, so yesterday I drew some kind of square picture, and now I only restrict to these two edges. Okay. And so now you can make the following funny argument. So you observe that if you remove this part where T has norm 0, then this thing is just X de Rham cross 0, 1. And similarly, if I remove this part where T has norm 0, then I just get X Hodge-Tate dagger times 0, 1. And so now my claim is that this gives me the following equivalences. Vector bundles on this filtered de Rham stack are equivalent to vector bundles on this full ut equals 0 thing, and also equivalent to vector bundles on this filtered over convergent stack. And so what's supposed to be the argument? Well, again, I use that vector bundles are somehow homotopy invariant, and that they spread out to sort of small open neighborhoods. And actually, I'm claiming that all of these three are equivalent to having a vector bundle just on the locus where both U and T have norm 0. And why is that? Well, if I have a vector bundle on this locus here, where U and T both have norm 0, it spreads out to a small open neighborhood. And then I can remove this locus, and well, I have something on some small part of this interval, and I just spread it out to the whole interval. So trivially, I extend trivially. And the same thing I do on this X de Rham plus part. I also get something on some interval, I don't know, X de Rham times 0 epsilon, and then I extend this thing trivially to X de Rham times 0.
Can I maybe ask what formally goes into this? Like, you can spread them out. I don't suppose it's just Nakayama's lemma.
Right. So I mean, there are two segments. The one is that if you have actually a perfect complex on X cross S Betty, then it's equivalent to just a perfect complex on X if S is contractible. And this is true in general for, say, contractible CW complex. And if S is too wide, then okay, but and X can be anything. And the second one is basically that if you have something like perfect complexes on something which looks like, so I have some Gelfand stack X, and I look at the locus where some function has norm 0, and I'm claiming that this is the same as the co-limit of the categories of perfect complexes on the loci where this function has norm at most epsilon. And for this, basically you need that. If you cover X by affines, then you can cover it by affines which don't become too animated. So it's some kind of flatness condition on a cover of X. And sort of in the end, using this flatness condition, you reduce to the affine case, and in the affine case, I'm just saying that if I have perfect complexes on the co-limit of some algebras, it's the co-limit of the category of perfect complexes on each individual one.
There's also some descent that goes into proving it for X, right?
Right, exactly. And that's why I was saying you need, like, if you want to do this descent argument and reduce to the affine case, you need to have some assumption on this check nerve or on the sort of hypercover that you're looking at, and basically the terms are not allowed to become too animated. If you have some bound on the truncatedness.
It's important to notice that it's not f equals 0, so it's not Nakayama or anything. It's really norm of f equals 0.
Yeah, it's norm
so
of
it's
f equals 0.
neighborhood.
So it's the overconvergent neighborhood of the vanishing locus of f.
Okay, I see.
So I guess this is the most important part. So that sort of really here you get the co-limit of these algebras, and you don't have to quotient out by something.
Okay, fine.
Right, so it's more like in the affine line I'm looking at sort of this QPX dagger thing, and not QP. Okay. Alright. And now, well, you get the following functor. We start with a vector bundle on X gram plus. Using this argument I just gave, it's equivalent to a vector bundle on this filtered overconvergent Hodge stack. And now I just restrict to the unfiltered one. So I restrict to the locus where, say, T has norm 1. And then using this map from Fontaine X diamond to X diff 1, I can restrict further to vector bundles on the overconvergent neighborhood of X diamond inside of Fontaine X diamond. I pull back along this map. And actually I only want to restrict to the formal neighborhood. This will be enough. So I can just do a further pullback. And so now, what have we obtained? Like this category is vector bundles with connection, filtered vector bundles with connection on X. This category is p-round plus local systems on the Proetile side. And my claim is that this composite functor identifies with the functor I wrote down before, using this OB drum period sheaf. Alright. And maybe I can at least give some sketch of how you do this. So the key point is that last time I told you that if X admits a toric chart, then you can describe this category of vector bundles on this filtered overconvergent of stack very explicitly. And you can also explicitly, in terms of sort of this linear algebra data, you can also say what pullback along this map does. And this is basically this equivalence. So maybe I should say first that the only mysterious thing in this diagram is this equivalence. And sort of these functors are not too bad. Okay. So really, you somehow have to understand how to go from filtered vector bundles with connection to something in here. And using the linear algebra description of this category I gave last time, and also using the description of this pullback functor, you can understand this in the case where X admits the toric chart. And maybe let me say what the key point here is. So recall that in this case, a vector bundle on the stack was something like a filtered object with backwards and forwards transition maps, plus a locally analytic action of the semi-direct product. Plus some condition on the Lie algebra action. That's induced by this locally analytic action. And now, let me at least say what the condition on the Lie algebra action coming from the ZP cross action was. So it was that if I should say it like this. If I look at the ith graded piece, then the generator of the Lie algebra of ZP cross acts by multiplication by, I think, I, plus or minus I, something like this. And so now, what you conclude is that this filtration splits ZP cross into variable, and even sort of And why is that? Because, well, if I look at this GRU IV as a locally analytic ZP cross representation, then there are no HOMs between different GRU I's, and there are also no higher X's. Precisely because these, like if I take two different I's, the Lie algebra action on sort of the tensor product of these two will be by a unit. So there's no Lie algebra conversion. And so once you realize that this filtration splits, you can make everything reasonably explicit and compare with like this formula. And maybe, okay, let me say at the end that well, you also have to check that this identification that you construct in the end glues across different toric charts. Okay? All right. Okay. So, what does this tell you? This shows that maybe I should say that if I that this functor that I had from vector bundles on the syntomification to vector bundles on xdiff1, which I recall was equivalent to vector bundles on Falk-Fontaine X diamond. So this already tells me that this functor factors over this category of the round vector bundles. Because you can precisely see that due to this identification, you see that any B-Duram plus local system that you get, if you come from the syntomification, will automatically be generically flat, in the sense from before. And the sort of filtered vector bundle with connection that it arises from is obtained by restricting your vector bundle on the syntomification to the filtered Duram stack. And so, now, well, I still haven't told you why this functor from this filtered overconvergent Hauck stack to the unfiltered version is fully faithful, nor why the essential image is precisely characterized by the Duram condition. But for this, now you can use that this functor of Scholze is fully faithful, and so it suffices to check that if I look at the category of vector bundles on this X Hauck state dagger stack, such that the associated B-Duram plus local system is generically flat, that this embeds fully faithfully into B-Duram plus local systems. Plus the essential image are the generically flat. Local systems. Okay, and I think notice that I'm only claiming this fully faithfulness for sort of vector bundles on the stack for which I know that the associated B-Duram plus local system comes from a filtered vector bundle with connection. I think in general this is wrong. Because well, here I took an overconversion neighborhood. And this B-Duram plus is more related to the formal neighborhood. And so apart from sort of the geometric Sen theory argument that I can always go from X diff 1 to Fark-Fontaine X diamond, there's also a claim here that I can go from some overconvergent version of B-Duram plus to just B-Duram plus. Okay, and this should only work if you start with certain reasonable vector bundles. And well, maybe I say how you can do this. And so here the idea is, well, maybe let me just say that you can do some explicit calculation with differential operators. To sort of, well, both of these things have kind of a p-adic filtration, and I want to reduce to the associated graded. And now the problem is that on this side, the p-adic filtration is not complete because I'm using sort of the overconvergent version. But sort of using this explicit calculation, you can check that in cohomology it doesn't make a difference. That sort of in cohomology, the p-adic filtration will be complete. Like sort of high, if you twist by t high enough, then cohomology vanishes. So you can reduce to the graded level, where you just need to check that this functor is fully faithful. And well, this is precisely geometric sun theory. Okay. So this was my proof sketch of the statement in the beginning. Maybe let me make a quick remark that using this, you can recover the Dram comparison theorem. Which, I don't know, maybe shouldn't be so surprising. So let me state it in the simplest case, where X is a smooth proper rigid space over QP. And then, well, the Dram comparison says that if I take Poitar cohomology of geometric Poitar cohomology of X, so of the base change to CP, and I tensor with B Dram plus, I tensor with B Dram, it's isomorphic to the Dram cohomology also tensor with B Dram. And I'm also claiming that this is compatible with the Galois action on this Poitar cohomology and on the B Dram, and with the filtration on B Dram and Dram cohomology. And now the proof is rather simple. So I look at the map from X to G spec QP, and I consider the push forward of the structure sheaf along the induced map on syntomifications. And I claim that because X is proper and smooth, E is perfect. And this I will explain in the second part. So I'm just using here that if X is smooth and proper over QP, then the induced map on syntomifications is cohomologically smooth and cohomologically proper. And so it preserves perfect complexes. Sorry?
Can vector bundles be understood as reflexive objects in this category?
For some duality?
Well, okay, whatever Verdier duality is supposed to be on this syntomification.
Maybe more like perfect complexes?
Yeah, okay.
Like you mean the swap, basically the swap objects?
Yeah, basically the swap objects. It's not strictly the same.
I mean, any perfect complex will be swap.
Okay.
Because the map is cohomologic, like X sin to QP sin is cohomologically smooth, and also QP sin to QP is cohomologically smooth. This I will say, like, in a minute. I'm not sure if these are all the swap objects, but it sounds reasonable. I'm not sure. Okay. So, right. I wanted to say that you can look at the restriction of E to QP Dram plus. So this will just be a filtered perfect complex now. And by proper base change, this will be the push forward along the induced map on filtered Dram stacks, again of O. And by the same argument, I can sort of pull this E back to a vector bundle on QP diff 1. And again, using proper base change, I find that this is the same as taking the induced map on diff 1 stacks and pushing forward O. So this is both by proper base change. sort of still using that this map on syntomifications is homologically proper. And well, then what I said before tells you that this QP Durand plus and well, maybe the associated B Durand plus local system of this Galois representation here are matched under this functor of Scholze. Okay. And you can check that this precisely amounts to this claim up here. And maybe I should say that also here there was nothing really special about the structure sheaf. So using the same proof, you get a version with coefficients, where by this theorem that I explained earlier, we now know that coefficients means Durand vector bundles on the Fag-Fontaine curve of X diamond. And you also see that I can easily do a relative version where I replace QP by some base S and assume that X to S is smooth and proper, and maybe I also want that S is smooth and partially proper over QP. Okay. Are there any questions? Then I'd like to move on to concave duality. All right. So maybe first recall from last time that maybe I don't want to write it down here, but
Sorry, just
yeah.
Reiterate. You're implicitly using this thing. So this E restricted to QP div 1 is supposed to be the left-hand side. This equivalent's like pro atol.
Yes, yeah, definitely, yeah.
Right. So you're using this correspondence.
Yes, yeah. I think I'm always using this.
Yeah, okay, but I just learned
Probably 5 to 10 places, yeah. But yeah. This is right. So yesterday I explained that there exists some reasonably nice presentation of QP, of the filtered prismatization of QP, maybe after I restrict to some open cover. Okay. And in particular, I also explained that for GM, sort of over this, I can look at the filtered prismatization of GM. And sort of the interesting part was over some open interval containing P under this radius map. And sort of the rest was just the prismatization. And this part I could somehow describe as a quotient of the perfected GM modulo a push out of ZPNA with GA dagger over GA dagger, where this was like multiplication by U. And maybe yesterday I had to put a bar here, but that's not too important. Okay. And using these presentations, you can prove the following statement. Namely that sort of, I guess, now I want to use this first presentation that I didn't write down. Using this one, you can show that QP sin is cohomologically smooth, so over G spec QP, over the point. with dualizing complex, the first Breuil-Kissing twist shifted by 3. And right, so basically the proof is you can check this on some open cover of QP-syn, and then sort of the most interesting part is this open interval around P, and there you use this presentation that I said last time.
Is this 3 supposed to mean something?
Yeah, so I was I was about to say something about the 3, because you might expect a 2, rather. But this 3 basically is, well, is here because you have an additional shift by 1. Because this QP-syn has like an extra topological direction. Which is basically all these like intervals that showed up in some of the arguments. Like these introduce an extra dimension, and this gives me another shift by 1.
When I try to think about like actual algebraic varieties, is this just going to like magically disappear, or does it have some meaning? Or is it?
I mean, sort of the appearance of this interval will change what compactly supported cohomology is. Right? I mean, it doesn't make a difference for the cohomology, but it will change the compactly supported cohomology, and so then you get an extra shift.
It is surprising. I mean, if you have something which is smooth and proper, and you're saying it would get a sorry.
Yes, but this is not proper.
Sorry, I meant something like it. Oh.
So this is the other thing, that this QP-syn is not cohomologically proper. It's only cohomologically smooth. So you really get something. You really get compactly supported cohomology on the other side of Poincare duality. And I would say heuristically this should be because this QP-syn is in some sense open inside the analytic prismatization of ZP. The analytic syntomification of ZP. And sort of, I would think that this thing should be cohomologically proper, and then QP-syn is open inside this, and this is why it's not cohomologically proper. This is at least the rough intuition that I have.
So there's like, I don't really understand this, but I guess you've written about this, but there's some weird mixture of like Banach-Kolmez spaces and regular Poincare duality when you study Poincare duality and Proital cohomology. Is that related to what's going on here?
Are you confused that it is a 3 and not a 2?
It's not related to the 3.
I'm just trying to understand.
It's not related to the 3, and sort of maybe Arthur César will not be too mad if I say this, but for QP diff 1, you get the same result with a 2, and this thing is cohomologically proper.
So for your Ducato, you get also a shift by.
So maybe just to follow up on Linus's question. I mean, I thought there are various results of like duality for cohomology, and there are various, but maybe so it's not SQP vector spaces, but it's in some other category of PC spaces or so forth. And but that's coming from the QP div 1.
Yeah.
And this is something else.
I think that's really a different phenomenon. And maybe again about this non-properness, the problem is that yesterday I had this kind of picture. Basically, the problem is that this picture is open towards the top, and or even you can even see this in the prismatization of QP. So if I do the prismatization of QP, my picture is open here, and it's open here. Being open here is fine, because this somehow is the P equals 0 locus, and so this just comes from the fact that I've base changed to QP. So this is just because I'm working over QP, where I can't see this thing. But the fact that I can't see this boundary is more serious, and this is somehow why this thing fails to be homologically proper. And exactly if you take the analytic prismatization of ZP in some sense, then this boundary is added. So this is why probably for ZP this thing should be homological. Okay. All right. So now, let me state the relative result, which sort of does not involve any confusing shifts, because this is somehow all absorbed by the base. So let's say I have fx to y, a map of Berkovich spaces, and then in part 1, if f is rigid smooth and pure of relative dimension n, d, then the induced map f sin on syntomifications is cohomologically smooth. And the dualizing complex is the d's by kissing twist shifted by 2d. Okay. And now if f is locally a finite presentation, but in a derived sense. So sort of you can allow like quotients by regular sequences. And quasi-compact, then f sin is cohomologically proper. Well, I guess there's some technicality that I should say weakly cohomologically proper, but it means that f lower star is f lower weak. All right. So in particular, this now justifies why before in this proof of the de Rham comparison, I got a cohomologically smooth and cohomologically proper map. And maybe let me say something about the proof. But in both cases, somehow you reduce to the case of GM by some more or less elaborate dévissage. And then again, the most interesting locus is in some open neighborhood of P, where you have this presentation. And well, proving that this thing is smooth is the hardest part. Because somehow here you take this infinite limit. And so a priori, if I just take this alone, it's not smooth. But somehow the idea is that the non-smoothness of this limit is counteracted by quotienting out the ZPLA. And more precisely, the idea is that you can approximate this quotient by sort of taking a finite stage of this limit. And then this ZPLA action will extend to the action of some slightly bigger analytic group. And well, then each of these approximations is cohomologically smooth. And well, the hard part is to show that these approximations are sufficiently close to what you actually want. And for this, you need, it's again some kind of Sen theory statement that like somehow doing lower star to all these approximations is eventually an isomorphism. So you use some kind of Tate-Sen formalism for this ZP action on this perfection genome. And a similar thing happens for QP. All right. Yeah. Right. Other questions? Then I state the last result. So now I want to say something about Chern classes. So my claim is the following. I have X a Berkovich space. And then there exists a natural map from, call this C1 syn. And it's a map from basically the étale cohomology of Gn shifted by 1. So in this Berkovich space business, there's some kind of difference between like rigid smooth and Berkovich smooth and rigid étale. And basically, this allows also for rational localizations. Whereas here, in this thing, I don't allow rational localizations. Because rational localization always means something overconvergent. And this should not be considered smooth. But here it is allowed. You can also just ignore this. And it goes to the syntomic homology of the first Brooke-Hissing twist shifted by 2. And if I look at relative projective space over X, I claim that to this point, I claim that you can describe the relative syntomic homology of this projective space using term classes. So, namely, maybe I just write it down. The formula looks a bit messy, but so basically, if I take the relative syntomic homology with coefficients in the dth Brooke-Hissing twist, and I shift by 2D, then this is just a direct sum of shifted Brooke-Hissing twists. And this isomorphism is induced by this Chern class here, where sort of here instead of x, you should now take px to the d. And here you take the class corresponding to the tautological line bundle on PD. And then it gives you something in H2 of O1, or sort of the relative H2 of O1. And this is precisely the map from O to this is a map like this. And sort of then you apply this to tensor powers and you get like all these maps. Right. And maybe let me say how this works. So how do I get this Chern class?
You should end a couple of minutes early because there is another
okay. Let me just say the key. So the key is to construct a map from the syntomification of GM to the classifying stack of GA twisted by 1. And then if you have a line bundle on X, you get a map X syn to point mod GM syn. And then composing with this map, I get a map like so, and this is exactly my Chern class. Okay. And well, again, for this, you use this explicit presentation, and now you see that it suffices to construct a map like so. And now I should have been honest and not suppressed twists on this side. So actually this ZPLA and this GA dagger, they should have some twists. And then for simplicity, let me ignore the twist on this side, and then everything comes out right. And, well, what's the map? GA. Well, there's a natural map from Zp at A to Ga. And then there's a map, and I multiply this by U. And well, I just take the canonical map from Ga dagger to Ga. And sort of these will glue to give me this map. Alright, so maybe, and then, so to check this statement about the cohomology of projective space, what you can use is that you already know that this thing will be a perfect complex because projective space is smooth and proper. And then I've told you before that perfect complexes can be described in terms of perfect complexes on the Hurokata stack and the filtered Ram stack. And so in the end, you only have to check this isomorphism for Hurokata cohomology and filtered Ram cohomology. And for both of these, like this is known. Okay, and I stop here.